All right. Hello, everyone. It's really great to be here with all of you today. My name is Mark Lohmeyer, and I lead the AI and computing infrastructure product team at Google. And to me, what's happening in AI right now, I mean, we're all kind of experiencing it. It feels a little bit like the early days of the internet, but what took probably many years back then, it feels like it's happening much faster now. We're seeing new breakthroughs. It seems like almost every week. Like I wake up on Monday and there's something new and amazing that's been enabled. For example, has anyone played with the new image model Nano Banana? Show of hands. Nano Banana. Pretty cool. So if you didn't raise your hand, you should check it out. Pretty awesome. So according to Ella Marina, it's the highest ranked image model available in the market today. And I'll give you an example of what it can do. So here, as a starting point, is a real, slightly pixelated photo of my dog, Chewy there. So Schnauzer. And using Nano Banana, I can really easily envision him in new scenes, like here, where he's competing in a dog show. I think he's going to win. Looks pretty good. And because the model is also really great at multi-turn generation, so I can go back and forth with it. So this is Chewy. He's exploring new career opportunities as a vibe coder. He's got his hipster look on there, so looking good. And then finally, you can add realistic text. So this is Chewy. He's pivoting now to becoming a tech influencer. So really popular career these days. So these are obviously sort of fun, cute examples, but more broadly, models like this are, of course, incredibly valuable across so many industries and so many fields. And so ensuring that we can deliver them fast, reliably, accurately, and very importantly, cost effectively at massive scale is really critical. So let's talk more about sort of how we're doing this, both internally at Google, as well as how we're making that available to our cloud customers and our partners. Now, we all know training the next gen model is really important. It's great. It's where it starts. But where the rubber is really hitting the road these days is inference. In fact, I believe that 2025 is really the start of, let's call it, the age of inference. And if you think about like the number of tokens that need to be generated and processed for experiences like Nano Banana and scaling that to millions or maybe in Google's case, billions of users, you can see why, right? In fact, at Google, from April of last year to April of this year, so 12 months, we saw a 50 times increase in the number of tokens per month that we processed across all of our products and services at Google. And then just 2 months later, so in June, that number skyrocketed to 980 trillion tokens in a month. That's a 2x increase in 2 months. So it's a big number. Put that in context. 980 trillion tokens. It's roughly the amount of information in a novel for every single person on planet Earth every month, right? And we're just getting started. So to keep scaling exponentially like that, and we definitely see that happening, we in the industry, all of us, obviously working together, need to deliver the next generation of AI-optimized infrastructure, specifically for inference. And, at top level from a business perspective, we need to deliver obviously a fantastic customer, fantastic user experience that drives business outcomes for our customers. But on the technology side, we sort of have two top level priorities, let's say. The first is how do we scale rapidly, but with great performance? But while at the same time also driving down the cost to serve, the cost per transaction. If you think about it, for most businesses, that's what determines how many customers they can reach and how can they grow their customer base and do that profitably. But interestingly, what's emerged not too long ago is a third and really critical constraint, which is power, energy. This has become one of the most precious commodities we have because the physical build out of the infrastructure is now actually starting to be limited by power availability. I think we all see this. So, at this scale we're talking about here and thinking about growing exponentially, we need to think about power efficiency more holistically. The old way that we and many others used to do it is we'd look at active chip utilization. We'd use that as a proxy for energy consumption. That really isn't adequate anymore. So 3 weeks ago at Google, we released a detailed technical paper. Check it out if you're interested in getting more specifics. But it looks at a much more comprehensive methodology for measuring power consumption, energy consumption, looks across the entire system and all the different dimensions that you see referenced here. So using this approach, actually, we found out something interesting, which is that a single Gemini prompt is substantially more efficient than what previously people might have thought publicly. It uses about a quarter watt hour of power, 30 milligrams of carbon dioxide, about 5 drops of water. So to put that in perspective, that's about the same amount of power as watching 9 seconds of TV. So today, one Gemini prompt, 9 seconds of TV. I'll leave it to all of you to decide which one you think is more valuable to you. I have my vote. So as these workloads continue to scale, we need to do even more to increase that efficiency beyond where we are today. And we need to do this across the full stack. So for example, things like new model architectures, mixture of experts, hybrid reasoning models, new software techniques, and we'll talk some more about these today, like disaggregated serving or speculative decoding. You're seeing that in the animation here, as well as inference-specific custom hardware. And you're seeing that come out across the industry now, as well as data center operations, how we're running those machines at large scale. And looking across the full stack and optimizing across all these areas can yield really, really great dividends. In fact, over the last 12 months at Google, we were able to drive down the energy consumption of a Gemini prompt, per prompt by 33 times in 1 year, right? And we need to keep doing that going forward as you think about the demand continuing to grow. So, given all we've learned here, what I'd like to do is share sort of a high-level view of our approach at Google to AI infrastructure, and then we'll dive a little deeper into each of these 3 areas. The first principle is really co-design across the entire stack. So from the research, model research, Google DeepMind, et cetera, to the software algorithms to infrastructure hardware, design across that end-to-end system. As one example here of how this can play out, when we built our first TPU-based system a little bit over 10 years ago now, it was really around solving some internal scaling challenges we had. But then when we put that compute power into the hands of our researchers in Google DeepMind and others, that really, in many ways, directly enabled the invention of the transformer. And as we all know, that's now the architecture today that's powering most of what we're doing with AI and Gen AI. So that's number 1. 2, as we talked about before, we really have this relentless focus on efficiency, data centers, power, everything we talked about before, but also the people and processes, and bringing to bear entirely new disciplines at Google. For example, you think about the invention of SRE many years ago. We need to do those same types of things in terms of how we're operating these large-scale data centers now for AI. And then third, an obsession with simplifying the path from a great idea. So, someone has a great idea in research to actually putting that in products and scaling that in production. How do we shorten the time to innovate there? And then how do we, once we find a winner, how do we scale it up rapidly and cost effectively at scale? So this is looking at our full AI stack here. I won't go through all the details, but the core point is that, we make this full set of capabilities available to our cloud customers, and they can leverage the capabilities and rapidly build at whatever layer makes sense for their business and delivers the most value to their business. So whether it's through an agent at the application level, whether it's through an API through our AI platform, models, data platform, they can come in wherever it makes sense for their business and leverage those capabilities. But of course, for today's discussion, all of this is powered by that infrastructure underneath that core foundation. And so let's go deeper now into that infrastructure. So at the center of our sort of top-level vision here is an integrated supercomputing system we refer to as the AI Hypercomputer. If you sort of build up the stack here from the bottom up, it includes AI-optimized hardware across compute, storage, and networking. On top of that, open software, which includes frameworks, compilers, and other capabilities. And on top of that, flexible consumption models, so new ways to consume this AI infrastructure commercially. And what we found is that in every single box that you see here, we're having to reinvent and deliver new capabilities, specifically optimized for the unique needs of AI workloads. They're so different than what came before. So we're innovating each box, but we're also optimizing across that full stack to deliver against use cases. So training, inferencing at scale, for example. And then finally, because we're Google Cloud, we deliver all this as Google Cloud services. So, how do we do that reliably, scalably, with great security built in and at the lowest possible cost? Great customer example here is Toyota. So they chose Google Cloud for a few reasons, but probably most notably ease of use and speed of scaling. This actually helped them reduce their model creation time by 20%. They also used a GKE, or Google Kubernetes Engine, which made the scaling 4 times faster than what they were doing before. And also notably, we actually enabled a relatively small team within Toyota to actually build their AI platform in half the time of what they expected for a project of this level of capability. So, this is just one of 1,000 customer examples, obviously, but I think it brings some of those benefits to the forefront. So now let's go deeper, right? Let's dive into each of the individual capabilities here, and we'll talk about how they come together specifically for inference. And we'll start with leading compute accelerator options. So you heard from Ian yesterday, hopefully all of you are for that as well. And, one of our most important and closest partnerships, I would say, from an ecosystem perspective is with NVIDIA. And at our high level, our goal in Google is to be first and best with NVIDIA. So we work really closely together with them across all of our teams, engineering, product, beyond, optimize together every layer of the stack. Of course, we leverage their awesome hardware, GPUs and networking, but also we integrate Google software and also NVIDIA software to deliver those solutions that I talked about together for our customers. And in fact, over just the course of this year, we've delivered 3 major new Google Cloud services that are based on the latest NVIDIA Blackwell platforms. So our G4 family, this is based on the RTX 6000. This is great for graphics, for Omniverse, and for cost-effective inference for smaller models. Our A4 service, which is based on the Blackwell 200. So this provides a actually fairly broad range of versatility for a broad range of AI workloads. And then on the far right, our A4X family of services. This is based on Grace Blackwell 200. And this is really awesome for cutting-edge models that require the highest possible performance at the highest level of scale. So this is great, and we really, really appreciate our partnership with NVIDIA delivering awesome capabilities for our customers. But we also offer the choice of our industry-leading TPU platform. And as I mentioned before, we've been innovating with TPUs for over a decade now, so over 7 generations with many technical breakthroughs along the way. You can see some of the specific examples here. And there really is no substitute for this level of experience and learning that you have to do as you iterate over 10 years to create these types of highly sophisticated systems. In fact, Gemini, and as I mentioned before, most of our models today are primarily trained and served on TPUs. So fast forward to today, latest and greatest on the far right there, our latest generation, the Ironwood TPU platform. This is the first TPU platform that we've built specifically for the needs of inference. So let's go deeper into Ironwood. We'll start with the chip. So the Ironwood chip, it delivers 5 times the peak compute capacity and 6 times the high bandwidth memory of our previous generation. This is obviously really, really critical for inference at scale. But let's go a little bit beyond the TPU chip and share some of the innovations that we're doing at a systems level that really make TPUs a leading platform for AI innovation for so many customers. The first area of innovation is how we scale and scale reliably. So with Ironwood, we've scaled to 9,216 Ironwood chips connected together into a single, we call it a superpod, leveraging our breakthrough interchip interconnect technology, or ICI networking. This allows those 9,000 plus chips to all work together and access a pretty staggering 1.77 petabytes of high bandwidth memory. With each HBM pushing 7.3 terabytes per second of peak bandwidth, really helping overcome data bottlenecks and other bottlenecks for some of the most demanding models out there. But what happens at this scale when something fails? And so this brings us to reliability. And if you think about it at this scale with this many individual hardware components, that many chips, never mind all the other components in the system, individual hardware component failures are actually a statistical certainty, right? It's going to happen. And so we need to do all sorts of things to make sure that we can abstract the user away from those underlying hardware failures. One capability here that's incredibly powerful is our optical circuit switching technology. So this acts as a dynamically reconfigurable fabric for that entire pod. So for example, if a node fails, OCS, optical circuit switching, it can rapidly reconfigure that compute slice, dropping the dead node and then seamlessly restoring the workload from a checkpoint so the model can keep being trained or being served. So it's this level of really, I'd say, deep systems level resilience that makes a super pod of this scale, right, the 9,000 plus, truly viable for mission critical workloads and applications. Another innovation is liquid cooling. So, at Google, we've been working on liquid cooling since 2014, so quite a while now. We had to do that in the early days to really scale with the TPU systems that existed even way back then. And we're now in our 5th generation cooling distribution unit, CDU, and we're planning to make available that spec to the Open Compute project later this year. To give you a rough idea of the scale here, as of 2024, we had around 1 gigawatt of total deployed liquid-cooled capacity, which was 70 times more than any other fleet at that point in time. So we created this first for TPUs, and now we're leveraging it for GPUs as well, of course. All right, so those are a few specifics, but if we zoom out a little bit here, you can see the full picture of a TPU superpod at work. It comes in 2 forms, a small one, 256 chips in a pod, or the large one that I talked about before. This is interconnected with 1.2 terabytes per second of ICI networking. And the scaling, by the way, you're just seeing the front of it here. Think about there's many rows of that behind that that come together to deliver 9,000 chips. But the scaling doesn't stop here. So with our Jupyter data center network, we can scale further across dozens of these superpods working together. And all of this hardware is optimized to work with leading frameworks, so both JAX and PyTorch. And notably on the PyTorch side, we're committing to a native PyTorch implementation on TPUs. So really embracing the PyTorch community and so many workloads out there that have been optimized over so many years for PyTorch, making it easy to bring those TPUs. So together, our work on systems and software here together, if you wrap it all up, big number, it's delivering 42.5 exaflops per pod. Pretty amazing. All right. So we talked a lot about accelerators. That's obviously a critical component. In many ways, it's the heart of these AI systems. But now if you think about inference, an inference solution requires more than just the accelerators to deliver that experience that I talked about before. And here's where, you might see some challenges. For example, staying up with state of the art is pretty hard. It seems to change every week. It's hard for all of us to stay up to date with all of the changes here. Second, there's switching costs. We all want this flexibility in these systems, but today, changing frameworks, changing hardware, frankly, it's too hard. And finally, with so many different possible deployment architectures, it's often hard to find just the right combination. And the wrong choice could cost our customers millions of dollars potentially. So it's really important to get it right. So obviously, we've thought a lot about this. How can we help? How can we help address these challenges? And so, here's a relatively simple picture of what we see as an optimized architecture for inference. So I'll go through this at a high level and then we'll double click in. So working from left to right, the inference request comes in. It goes first to GKE. This is Google Kubernetes Engine, GKE Inference Gateway. This can route that request based on the request parameters, also the load on the system, to the right pool of accelerators. Models are deployed to GKA clusters you see in the middle here. Those have now first-class support for VLLM as a model server, so this enables compatibility across GPUs and TPUs. Customers can use a dynamic workload scheduler. This is a new flexible commercial consumption model we created just for the needs of AI to make sure the capacity is available in those node pools. And then finally on the far right, leveraging AI-optimized cloud storage to store the model weights, cast the data, and many more. So this is really a top-level view, bird's eye view of an end-to-end system, but let's go deeper now into each of these individual technologies one by one, and we'll talk about how they can be used end-to-end to serve a simple agentic workflow. So let's start with 2 new pretty awesome advancements from our Google Kubernetes Engine team, Inference Gateway and Inference Quick Start. All right, so let's say a new user request comes in, and immediately we're faced with a challenge, which is, think about it, traditional load balancing was not designed for the needs of AI workloads. With AI, a single prompt can trigger one of these large multi-step reasoning processes, and it can overwhelm one server while others potentially could be sitting idly by. This leads to unpredictable latency and efficient use of those valuable resources. So to solve this challenge, we created a first-of-a-kind solution called GKE Inference Gateway. It uses AI-aware routing and also AI-aware load balancing techniques to even out the utilization across those node pools so those incoming requests don't queue up, and you've got a nice balanced utilization across your accelerators. Here's an architectural view of that. So Inference Gateway will continuously monitor your model servers and analyze metrics like pending request queue length or KV cache utilization or others before selecting the ideal node to route a request to. So I'm really excited today to announce that we're making the GKE Inference Gateway generally available. So it's out there to give it a try if you'd like. Pretty awesome. Along with two new capabilities built in. So the first is prefix-aware routing. So for an application like multi-turn chat or document analysis where you're reusing the same context across multiple prompts, now you can route those requests to the same accelerator pools that already have that context cached. You can see how valuable that would be. The second is disaggregated serving, obviously a big topic for this week. But this is a technique that separates the initial processing of a prompt, so the prefill stage, from the token generation or the decode stage. And since these two different stages have pretty different resource needs and actually based on the workload might need to scale differently as well, you can now run them on separate optimized machine pools for both and scale them also independently of each other. So these capabilities are super powerful, but I'm sure sometimes it feels a little bit overwhelming to be constantly told, hey, you've got to use this new technique, that new technique, or you're going to fall behind. And we struggle with this too internally. So this brings us to Inference Quick Start. So think about Inference Quick Start as a database of tested inference configurations. All you need to do is tell it about your needs. So what models you're using, what are your priorities for latency, cost, other things, and it will give you a set of recommendations based on best practices and actually the latest benchmarks that we've run within Google on those various combinations. So you can deploy those best practices right out of the gate. And then, because you need your needs and the workloads are always evolving, we're also monitoring the system over time, those inference-specific performance metrics that I talked about before, so you can dynamically fine-tune your deployment over time as maybe the workload needs change or the model changes. So you can make sure you're always up to date easily. All right, so a little bit on the technology, but what are the benefits here? So pretty significant. Taken together, these can deliver up to 96% lower latency at peak throughput. This is great for highly interactive, responsive workloads like interactive coding, agents, etc. Up to 40% higher throughput, which is great for prefix-heavy workloads like knowledge base analysis. And all of this was up to 30% lower token costs per token. We talked about how important that was before. All right, so that's Inference Gateway. So it's intelligently routed that request. Now we face another critical question, which is, do you have the accelerators when and where you need them? And look, even today, getting capacity can sometimes be a struggle, right? You can either over-provision those resources and waste money, or maybe under-provision, and then you're leaving your research team or your customers waiting. So this is where Dynamic Workload Scheduler, or DWS, comes in. It's a new commercial consumption model we created specifically for the needs of AI workloads. So it complements on-demand, spot, and the other traditional consumption models that you can also still use. And it helps in two ways. So first, for time-flexible jobs, we have the Flex Start mode that lets you queue up your experiment or your request, and we'll run it for you as soon as those resources are available across all of Google Cloud, based on the policies you've set. And then secondly, for critical time-bound projects, we also have something called calendar mode. So think about this. It allows you to book capacity like you'd book a hotel room. You say this many resources in this location for these dates, and we guarantee that those resources will be available when you need them. You won't get preempted, and you only have to pay for them, obviously, when you're actually using them. So really bringing the benefits of cloud to bear here for AI. All right, so with that in place, the next question is, hey, which accelerator is actually right for my workload? Which GPU, so many different GPU options, or which TPU, so many great TPU options out there. So earlier this year, we announced that you can now easily run inference on TPUs because we've enabled VLLM to work on TPUs. As well as, of course, it already worked on GPUs, right? So fantastic way to get flexibility across TPUs and GPUs and effortlessly switch between them now with just a few configuration changes. And to further simplify, we've introduced something called custom compute classes. So think about these are profiles that you would use to tell GKE's autoscaler what type of virtual machine nodes and what consumption models to use and in what order of preference for your workload. So for example, you could say, hey, I want to start first with my top priority is GPUs, a spot. But then if I don't have enough of that, let's fall back to GPUs on demand. And maybe if I don't have enough of that, let's fall back to TPUs on demand. You can decide what makes sense for your business. But they're all now in the same deployment, and GKE Autoscaler can honor those priorities and automatically scale based on the dynamic needs of your workloads. So pretty cool stuff. So speaking of GPUs, we're excited to announce that we partnered with NVIDIA to bring NVIDIA Dynamo to Google Cloud. This gives another powerful integrated option for your inference workloads. And our joint customer Base 10, I think you saw maybe yesterday too, is running Dynamo on Google Cloud with NVIDIA GPUs with really great results. So now let's talk about another key requirement for inference, which is getting those hungry, super valuable accelerators well fed with data. This is a pretty common issue these days, frankly. If you think about inference and your GPU or TPU capacity might be distributed across different regions around the world, maybe different from where your core data is actually stored. And that type of latency that you could have hit there could really negatively impact performance. And for something like a large model, even just loading the model weights sometimes can take tens of minutes. You think about the need to dynamically scale, that makes it sort of a non-starter, right? If it takes 10 minutes to load new model weights. So that's precisely why we're investing so much heavily in optimizing our storage services for AI. Earlier this year, we announced Anywhere Cache. So this is a new, fully consistent read cache that works with your existing Google Cloud storage buckets, and it caches the data within the same zone as the accelerators automatically. This can reduce read latencies by 96%. It also can reduce the network costs because you're not now having to go across the network to access that data. So let's make that a little bit more real, right? So imagine you're a developer, you're using a coding assistant, you type in a request and pause, and you get a pause waiting for the code suggestion to come back. You know, that pause, even if it's just a few seconds, it's friction for the developer, right? It hurts productivity. Now imagine that interaction is 96% faster, and that suggestion appears almost instantaneously, sub-second, let's say. You know, that's what keeping that data cached close to those accelerators looks like. And we all know that's not just a nice to have these days, right? Those delays can break a user's flow. And so we're really focused on making these interactions as real time as possible. Just ask our friends at Anthropic. As you can see here, they also ran into that problem, which is why they are actually now using Anywhere Cache to co-locate data with their massive TPU clusters for their model Claude. This enabled them to actually remove their own complex do-it-yourself caching solution, and now they can dynamically scale reads up to 2.5 terabytes per second. In addition, for workloads with long context windows that exceed the memory that's available in the GPUs, you can also take advantage of managed Lustre. This serves as a high-performance storage resource to satisfy key value requests, keeping those GPUs well saturated with ultra-low latency and millions of IOPS per second. And finally, tying all of this together, can't forget about the network, is Cloud WAN. So this is our fully managed global network. Cloud WAN helps across many domains, but in the case of AI, it helps customers that need to access AI computing resources across different regions, maybe different clouds outside of Google, multi-cloud environments, as well as on-prem environments. And so what it does is it allows you to connect the models to the data, wherever that data is, some other cloud, on-prem, wherever, as well as connect the models to the actual users, wherever those users are distributed around the world. And because this is built on our planet-scale networking infrastructure, it can deliver 40% improvement in the application experience and 40% lower TCO compared to traditional bespoke WAN solutions. Wrapping it up here in summary, you know, what have we sort of walked through here? Well, you know, maybe a simple way to think about it is it's a blueprint for state-of-the-art inference, which can really be tailored uniquely to your environment, your needs, and your use cases. And all the technologies I've shown here, you know, went kind of deep, but they've been designed to help deliver on those original requirements that we started with for inference, right? How do you deliver a great user experience, low latency, great performance with leading edge models? How do you scale that? And how do you do that with high efficiency, high energy efficiency, and the lowest possible cost per transaction? You know, it's the same approach that powers all of our Google AI services internally, and now you can take advantage of it also to power your business, deliver real value to your customers, innovation to your customers, and scale for them. So we talked a lot about here, we covered a wide range here at a high level, but to learn more about how Google can help support your AI projects or how we can maybe partner together if you're an ecosystem partner, we have several deep dive sessions later today and throughout this week. So please, we'd love to see you come by the booth, see some of the sessions that you see here. And with that, I'll say thank you very much.